Welcome to Frontiers of Research. I'm Antoni, and today we're exploring one of mathematics' most captivating stories, the Poincare Conjecture. We're joined by Dr. Rachel, our topology expert, and Josh, who will help us navigate this fascinating mathematical landscape. This conjecture, first proposed by Henri Poincare in 1904, stood as one of mathematics' most challenging problems for nearly a century before its dramatic resolution by Grigori Perelman in 2002. It's a story that touches on the very nature of space itself and showcases both the depth of mathematical thinking and the sometimes surprising paths to mathematical truth.
Henri Poincare was truly a mathematical giant of his time. In the late 19th century, he essentially created the field of topology, the study of properties that remain unchanged when shapes are continuously deformed. His work on what we now call manifolds was revolutionary. The conjecture arose from his study of three-dimensional manifolds, particularly what we call the three-sphere. What's fascinating is that Poincare actually first proposed a false conjecture, found a counterexample himself, and then refined it into what we now know as the Poincare conjecture. This kind of intellectual honesty and willingness to publicly correct oneself was characteristic of Poincare's approach to mathematics.
Could you break down what exactly the Poincare conjecture states? I know it has something to do with spheres, but what makes it so fundamentally important in mathematics?
The conjecture, at its heart, is about recognizing when a three-dimensional shape is essentially a sphere. More precisely, it states that every simply connected, closed three-manifold is homeomorphic to the three-sphere. Let me explain what this means in simpler terms, starting with the two-dimensional case. Remember that a sphere in 2 dimensions is just a circle, a one-dimensional loop in the plane. Imagine drawing any closed loop on a surface. If you can shrink that loop down to a point without tearing it or having it leave the surface, and you can do this for any loop you draw, then the surface must be equivalent to a sphere. In 2 dimensions, this is easy to prove because we can always push any loop outward into a nice round circle shape and then shrink it down. But in 3 dimensions, we lose this clear visualization. We can't see the whole shape at once, and we have many more directions to consider. The conjecture suggests that this same property of being able to shrink loops still determines the global shape, even in 3 dimensions.
The history of attempts to solve the Poincare conjecture is fascinating. Rachel, could you walk us through some of the major developments and attempts over the decades?
The major breakthrough came in the 1960s when Stephen Smale proved the generalized Poincare conjecture in dimensions 5 and higher. Michael Friedman then solved the 4-dimensional case in 1982, earning him the Fields Medal. But the original 3-dimensional case remained a challenge. It was William Thurston who provided a new perspective through his geometrization conjecture in the 1970s, suggesting a possible path to the solution.
Could you elaborate on Thurston's contribution? How did his geometrization conjecture relate to the Poincare conjecture?
Thurston's geometrization conjecture provided a grand vision that included the Poincare conjecture as a special case. He showed that all 3-dimensional manifolds can be broken down into geometric pieces, each with one of 8 possible geometric structures. These include spherical geometry with positive curvature, like a ball, hyperbolic geometry with negative curvature, like a saddle, and Euclidean geometry, which is perfectly flat. Then we have the product geometries, S2XR, which looks like a cylinder, H2XR, which combines hyperbolic space with a line, and the Néel geometry based on the Heisenberg group. The last two are the Soule geometry and the SL2R geometry. This insight opened up a powerful new approach, using geometric flows to gradually deform manifolds into these standard geometric pieces.
This brings us to Richard Hamilton's groundbreaking work on the Ricci flow in the 1980s. Rachel, could you explain how this set the stage for Perelman's eventual solution?
Hamilton's introduction of the Ricci flow was revolutionary. This geometric flow, similar to how heat spreads through a material, smooths out irregularities in the geometry of a manifold. Hamilton showed that under Ricci flow, manifolds tend to become more regular and uniform. He proved several crucial results and developed many of the technical tools that would later be essential. However, he encountered serious difficulties with the formation of singularities, points where the flow breaks down. These singularities were one of the major obstacles that prevented a complete proof.
And this is where Perelman comes in. How did he manage to overcome these obstacles that had stumped everyone else?
Perelman's breakthrough came through a deep understanding of these singularities. He developed new techniques for analyzing them, including what he called surgery on the Ricci flow. When singularities form, his method essentially cuts them out and continues the flow. He also introduced the crucial concept of entropy for the Ricci flow and showed how to control the topology through these surgeries. What's remarkable about his proof is that it's not just a solution to the Poincare conjecture. Einikhoff's Thurston's entire geometrization conjecture. His 3 papers, posted on the Mathematics Archive between 2002 and 2003, were revolutionary not just in their results, but in their techniques.
The verification of Perelman's proof was itself a fascinating process. Could you tell us about how the mathematical community responded and verified this momentous achievement?
The verification process was intense. Several teams of mathematicians worked to understand and verify Perelman's arguments. Notably, Poincare and Shiping Zhu published a complete exposition, as did John Morgan and Gang Tian. Bruce Kleiner and John Lott maintained an online commentary explaining the proof. What's particularly interesting is that Perelman's original papers were quite sketchy by mathematical standards. He provided the crucial ideas and left many details to be filled in by the community.
There's a famous illustration from Science magazine that shows a sequence of shapes evolving under Ricci flow. Could you explain what we're seeing in this sequence? Particularly the color changes from red to blue and those dark rings around each shape.
This illustration shows the evolution of a shape under Ricci flow. At the bottom, we see a red spherical shape. As we follow the sequence upward, the sphere stretches and develops what we call a neck in the middle, eventually becoming more like a dumbbell shape at the top, shown in blue. The color gradient from red to blue represents curvature. Red indicates high positive curvature, like on a sphere, while blue shows areas of lower curvature that develop as the shape stretches. Those dark rings you noticed are actually regions of particularly high stress in the manifold, where the curvature is changing rapidly. They help us visualize where the neck-pinching singularity is likely to form. When the neck becomes too thin, as shown in the blue dumbbell shape at the top, this is where Perelman's surgical technique comes in. At this critical moment, we perform surgery by cutting along the pinched neck and capping off each end with spherical caps. This effectively splits the shape into 2 separate spherical manifolds. What's remarkable about Perelman's insight is that he proved this surgery process preserves all the essential topological information about our original manifold. The dark rings in the illustration help us identify exactly where this surgical intervention should occur.
Beyond solving this specific conjecture, how has this work influenced mathematics more broadly? What new doors has it opened?
The impact has transformed mathematics. The techniques developed for this proof have found applications across mathematics and theoretical physics. The study of geometric flows has expanded dramatically with applications in differential geometry, mathematical physics, and even applied mathematics. The methods for handling singularities have influenced many areas of partial differential equations. What makes Perelman's work so remarkable is his novel combination of different mathematical approaches. He combined analytical techniques for studying flow evolution, geometric insights for understanding singularities, and topological arguments for proving his surgery-preserved shape. This synthesis opened new paths for exploring similar questions in other dimensions and geometric structures.
Thank you, Rachel and Josh, for helping us explore this remarkable mathematical achievement. The story of the Poincare conjecture, from its formulation to its solution, exemplifies the deep beauty and challenge of mathematical research. From Poincare's initial insights through Hamilton's groundbreaking work to Perelman's revolutionary solution, it shows how mathematical understanding grows through collaboration and persistence. Join us next time for more explorations at the frontiers of mathematical discovery.